Good morning and welcome back to College Algebra, Math 1313. Today we're going to be looking at other types of equations. As we get close to finishing chapter 2, we're going to look at a ton of different types of equations we can solve. So we've already looked at linear equations and then quadratic equations, and today we're going to be looking at a slew of other types of equations and how to solve them. Again, an encouragement, read through your textbook, try some of these practice problems before watching and way before attempting your homework and other assignments. That way you can do as best as possible on them. And let's get started. So today, there's really three types of equations that we're going to try to nail down. We're going to work through rational exponents. We're going to work through a type where you do U substitution, which is this quadratic-esque type of solving. And then the third one we're going to try to work through is radical equations or square root equations when there's more than one square root in your equation, and you have to work with that. So let's get started first with rational exponents and see some properties of exponents play out. So I put a number of different types of ways to look at exponents up here that all follow exponential properties. Properties of exponents is always a tough topic for people. There's a number of them. For example, x to the 0 equals 1, or x to the negative a is equal to 1 over x to the a. Things like this that play out as we see just different types of properties happen. If you need practice with exponential properties, you can go back and look at a section in chapter 1, watch some of their videos, or you can go and Google on YouTube the properties of exponents, and there'll be so many different videos that you couldn't watch them all in your whole life. So let's try this first one and just look and see what's happening with this exponent and how we might solve it. Actually, this one's not even a solve. This is just what's happening in this exponent. So 64 to the negative 1/3, the first thing I'm going to apply is this property that says x to the negative a is equal to 1 over x to the a. All that negative does is say, I don't like being negative. I'm going to go to the other side. I'm going to go to the bottom. And so what that means is I can rewrite this whole equation as 1 over 64 to the 1/3, and the negative went away. It went and hid. That is an equivalent equation. And now I can ask myself, well, what does to the 1/3 mean? Well, to the 1/3 just means the cube root, just like to the 1/2 means the square root. And so I'm asking myself, what times what is equal to 64? You say, well, 1 times 1, this is how I like to do it, just start at 1 and move up. 1 times 1 times 1, no. 2 times 2 times 2, that's 8, no. 3 times 3 times 3, 27, no. 4 times 4 times 4, 4 times 4 is 16, times 4 is 64, so we're looking at 1 over 4 as a simplified 64 to the negative 1/3. Now that's just a little practice with properties of exponents. Now we're actually going to solve. When we've got this solve, we're like, ooh, I don't know how to get that exponent to the other side, and that's the main thing that we're going to apply here is you've got an exponent, and I can't just square root it, or I can't just unsquare root it. It's an exponent with a fraction, and rational exponents are a little tougher to get rid of. So what we're going to do is we're going to have to get rid of it using a property that says if you've got an exponent exponented, so an exponent inside of an exponent, the two exponents just multiply by one another. So an easier way to look at that is x to the a to the b is equal to x to the a times b. This property is going to help us a lot because it's going to help us choose our exponent. Because now if I multiply those two exponents, because I chose the reciprocal, our new exponent is going to be 1. And just like every other equation we've done in this class, what you do to one side, you have to do to the other. So I chose that exponent specifically, I chose that reciprocal exponent so that 3 times 2 is 6, 2 times 3 is 6, and we end up with x to the 6 over 6. I'll do a middle step, hang on. That ends up with x to the 6 over 6, which actually is just x to the 1, which is just x, equals 125 to the 2/3. Ooh, now we have to solve that. 125 to the 2/3. There's two ways you could do this. You could do the top first or the bottom first, it doesn't matter. But what we need to accomplish is we need to square, because that's what the top says to do. The top says to square it, and we need to cube root it. That's what the bottom says to do. Me, I prefer to do the cube root first because it means we're working with lower numbers. So I'm going to write an equal sign and keep going. X equals, I'm going to write this as 125 to the cube root. Then I'm going to use that same property to break up the fraction. I'm going to say squared. And now if you look at that exponent, that property that we just talked about a second ago, I used the property in reverse to break apart the fraction so I can do it in 2 steps. The first step being a little easier. The cube root of 125 is 5 times 5 times 5. So we're left with 5 squared, which is just 25. Ah, we've done a solve now. So we've solved a rational exponent. And we did the first problem, which was just simplifying rational exponents. I'll leave this one. This one might only have one extra step, which is to move that 5 over. So I'll leave that for you. And we will move on to another type, which is radicals. I'm going to skip this one, though it's a little easier. Leave this for you to practice because I really need to do this type of problem, which is always classically a longer problem for students. It involves doing foiling and the quadratic, solving quadratics twice. And so I'm going to do this one real quick. I might go a little fast. If you want to slow it down or take pauses, you can. But I'm going to do it pretty quick. That way I can show you an example of it and you can follow along. It's also in the completed notes. But that way you have an example of this pretty tough one. So we'll get started. What I'm going to do first, I'm going to get these radicals on different sides just by moving it over. I'm going to write pretty small too because this one takes up a little bit of room. None of the math is new or difficult. It just takes up a little bit of room. And now how do you get rid of a square root? Well, you square it. Now it's really nice on the left side because it just leaves us with 3x plus 7. But on the right side, it's a little more annoying because we've got to do our FOIL, our first, outer, inner, last, right? So technically I'm going to rewrite this because isn't that just the same thing as it times itself, which helps us see the FOIL a little prettier? And now if we FOIL that term, we end up with, let's do this, first 1. Outside, negative the square root term. Inside, it's the same thing, another negative the square root term. And last, a square root times a square root just gets rid of it, and a negative times a negative is a positive, so we're just going to end up with plus x plus 2. And now we're going to combine like terms and treat this like any other problem. 3x plus 7, all the like terms are combined. The 1 can probably combine with the 2 to turn into a 3. The 2 square roots can turn into negative 2 square root terms. And then we've got an x just kind of hanging out by itself way over there. Okay, now before we get too crazy, we're like, oh no, what do I do now? Well, we need to get these x's together. We still need to combine like terms. And so I'm going to move over one of these x's. And I'm going to move over this 3. And what you do to one side, you have to do to the other side. Make sure to line them up with their like terms, same variable, same exponent. Those are going to cancel out or turn into 0 because 3 minus 3 is 0. We're going to be left with 2x plus 4 equals negative 2 root. We're getting close to getting this root out of here, which is going to be awesome. That's what our goal is. We got rid of one of the roots. Now our goal is to get rid of the other root by squaring someday. But I want to make it as easy as possible when we do that square. So I'm going to do one more move and get that negative 2 to the other side. And maybe I'll simplify first even. So now we're left with, what's 2 divided by negative 2? We've got a negative x minus 2. Remember, you're distributing. Pretty common problem is, oh, which one do I cancel or do I do them both? Division works just like multiplication, and you're distributing that division across the plus sign. Division, much like multiplication, is just distribution across addition or subtraction. And we're left, those do go away. They turn into 1. And now we've got a problem that we can get rid of a square root on. Square. Square. And we're finally going to get to a problem we can solve. So we're going to do FOIL one more time, which that's what I was saying at the beginning. This one has 2 FOILs, which is a little annoying. And we're going to end up with x squared plus 2x plus 2x plus 4 equals x plus 2. Because that square took care of that square root. And the left term got FOILed, keeping track of those negative signs and how they went away when you multiply a negative by a negative. So we've got x squared plus 4x plus 4 equals x plus 2. I did a little combining like terms. Now I'm going to move some terms over to get a 0, and that'll take us back to last week when we learned about quadratic equations. We've got 4 minus 2 is 2, 4x minus x is 3x, and x squared stays by itself. And we've got a 0 on that term. This is a nice, neat factor where the 2 breaks down into 2 and 1. And do 2 and 1 add up to be 3 in the middle? They absolutely do, so we can just leave it at that. X plus 2, x plus 1 equals 0. Now we've got 2 fully factored form with 2 factors. we can write down our solution set of x equals -2 and x equals -1. Awesome. But wait, because we had a square root and we did so much square rooting and unsquare rooting and re-square rooting, there's a really important thing that we need to look at, which it talks about up here in solving a radical equation. This last step is really important when you're working with radicals. We need to check our solutions because sometimes they're going to result in solutions that do not work or solutions that result in a negative square root. And that in that case, we cannot have that be a solution. And so, with this solution set of potentially -2 and -1, I'm going to go back to the square root and check it out. I'm going to go back to the original equation and plug in -2 and -1 and see what happens. So here's my check for solutions outside of the bounds, or solutions that result in a negative square root. So the first thing I'm going to do, let's do -1. It seems a little easier. Square root of 3 times -1 plus 7 plus the square root of, what was it doing, -1? -1 plus 2 equals 0, equals 1. Just a nice check. That would be the square root of 3. It's kind of tough. So, oh, no, that's 4. Square root of 4 plus the square root of, what's 2, 1 equals 1. So we've got 2 plus 1 equals 1. Uh-oh. That doesn't seem right. All right, so I'm going to tentatively cross out, making sure I did all my algebra correctly, that -1 solution, and I'm going to check this -2 to see if we've got another bad solution. So let's do it again. We're going to check square root 3 times -2 plus 7 plus root of, what are we doing, -2? Root of -2 plus 2 equals 1. And so we end up with a big square root. 7 minus 6 is 1. Plus 2 minus 2 is, 0 equals 1. Oh, sweet. We've got ourselves the correct solution. So that one did check out. Yes. And so we're left with one real solution, or one actual solution, which is -2. Because that -1 did not work. Just because it came out in our math at the end doesn't, when we're working with these square roots and these radicals, we really have to go back and check, because we could have at some point gotten rid of a square root and treated it as a positive or a minus. Have you ever seen that quadratic formula where you have the plus or the minus sign there? It really matters which one you're working with, and that is the reason we have to check our solutions. And all right, last thing we're going to do today. We are going to look at solving a quadratic with u substitution. And this is when we've got a quadratic that looks almost like a perfect form, but it's not. So like, for instance, this kind of looks quadratic-y because look, I got an a value that's missing. That's pretty common. I've got a b value with a coefficient. I've got a c value, and I've got a 0. But the only problem is those exponents, right? So here's what we're going to do. We're going to take those exponents, and we're going to chop them in half somehow, right? And here's how I'm going to look at it. I'm going to say, what do I wish was right here? You know what I wish was right there? I wish it was just a regular x. Well, I'm going to make it a regular x. But to avoid confusion, I'm not going to call it x. I'm going to call it u, because all the math worlds decided that u substitution is the name we give this thing. So if u equals x squared there, that means it has to equal x squared over here as well. And so what I've got is, I'm going to rewrite this as x squared, using that same property from earlier today, minus 8x squared, put it in parentheses so we can see the u happen. And now I'm just going to throw that u in there and do a normal style solve. u, I'll leave it red, squared minus 8 minus 9 equals 0. We got ourselves a quadratic equation that we can solve. So there we go. We're going to go to that 9. We're going to say, are there factors of c that add up to b? -9 and 1. Multiply those, you get c. Add them together, you get b. Looks like we got ourselves a u minus 9 and a u plus 1 equals 0. And now we can apply the zero product property from the very beginning of quadratics to solve for u, which means that u equals 9 and u equals -1. But wait, the problem didn't ask us to solve for u. The problem asked us to solve for x. And so we're going to take our original u sub and bring it back down here to both of these problems. We're going to say u's not actually u. U is actually x squared equals 9, and x squared equals -1. And then we can solve our equation. Say, how do you get rid of a square? You square root it. We got ourselves x equals plus or minus 3. Remember, if you introduce the square root, then you should introduce a plus or a minus. And x equal, plus or minus the square root of -1. Give you a second to think about what that is. Plus or minus I, an imaginary root, totally allowed. We got a degree 4 polynomial. We probably should have 2 imaginary roots and 2 real roots, given where this graph lies on the Cartesian coordinate system. And then we'll write our solution set. -3, 3, -I, I. Awesome. And I might ask, did it ask for real solutions? Because we learned about imaginary numbers versus real numbers. Didn't it specify real solutions? If it would have said, give us the real solutions, you might not include those i's on there. But since it just said solve, I'm going to include those complex numbers in my solution set, even though they don't show up on the normal graph. They don't show up on the normal XY graph because they're imaginary, and this is a real graph. So there's a solution set for Triad 8. And those are the main 3 types of equations that I wanted to go over as you work through your homework set. This one is, we've already done rational equations where you have to find the lowest common denominator and then multiply across the top on both sides. The only difference here is it's going to lead into a quadratic now that you have that in your toolkit. Now that we've done quadratics and we've done rationals, sometimes they like to combine them. So I'll leave that for you to practice and look at the completed notes if you want to see some solutions to that. Read through your textbook, read through the completed notes, rewatch some of these videos if you need to as we prepare for finishing up Chapter 2 and approaching the Chapter 2 test. Thank you very much. Thank you for watching, and I will see you tomorrow.